Hi, my name is Natalie Popescu, and I will be presenting the work of myself and my collaborators, Ziyang, David August, and Amit Levy from Princeton, and Sotiris Apostolakis from Google, titled Safer at Any Speed, Automatic Context-Aware Safety Enhancement for Rust. So, in practice, developers make a lot of safety performance trade-offs. A prime example of this is bounds checking, which is used to make sure that a value or variable is within some bounds. For example, checking that an index is within the length of an array. Bounds checks might need to be performed at runtime, and so they can add overhead. This overhead can come from simply the instructions added, or from missed optimization opportunities that the bounds check prevents the compiler from recognizing. If performance is a priority, then eliding bounds checks can re-enable missed optimizations, but also leaves the program vulnerable to buffer overflow attacks. Rust is a relatively new systems programming language that enforces memory safety, including bounds checks, by default, unlike C or C++, which do not. This property would prevent devastating security vulnerabilities like Heartbleed by construction. But we still see that developers manually circumvent these checks for performance. In the randHC Rust library, we see a comment that says, "It would be great if the bounds checks here could be optimized out, and we would not need unsafe. This improves performance by about 7%. In Firefox, we see another comment that says, "This function skips the bounds check in optimized builds. Using it at the hottest 2 call sites gives a 15% parsing speed boost." Yet, it's still an ongoing debate whether manually circumventing these checks actually improves performance. An example of this that we ran into ourselves is from a research paper published about a year ago, stating that unsafe memory accesses with get unchecked are 4 to 5 times faster than safe memory accesses with bounds checking. We tried to reproduce this statement with the version of the Rust compiler that we were using at the time, and we were unable. We eventually isolated a version of the Rust compiler for which this statement was true, but this begs the question, when does circumventing safety for performance make sense? The key idea of this work is that context changes the importance and impact of bounds checks. The simplest way to understand context is through application context. Let's take 2 different applications that depend on the same set of libraries, one that prioritizes safety and another that prioritizes performance. The developer of the safety-oriented application will likely want the maximum safety offered by the programming language, meaning that they will want bounds checks enforced everywhere in their application context. The developer of the performance-oriented application may want the extreme opposite to maximize performance, meaning that they may want any bounds checks that significantly affect performance elided in their application context. In reality, library developers have the option to elide bounds checks, and they make those decisions based on conflicting goals. Because both safety and performance-oriented applications often depend on the same set of libraries, we are stuck with the bounds checking decisions made in library dependencies. If the safety-oriented application happens to depend on unchecked indexing, there is no easy way for the developer to reintroduce bounds checks, and there isn't even a good way to make developers aware of the unchecked indexing their applications might use. Another way to understand context is through compiler context. Going back to this paper quote, we can already begin to see how the overhead of bounds checks may change per context, since the statement is true for one compiler version but not for several others. Another example is, if a library developer wants to write some array copy function like this, they may notice that this implementation is unusually slow. The library developer may then elide the bounds checks through unchecked indexing and find that the resulting implementation is 7 times faster than the safe one. This is because the bounds check in the safe version inhibits vectorization, while the lack of bounds checks in the unsafe version allows LLVM to recognize the code pattern and optimize the function into a memcopy. In this case, it's clear that the unsafe version is correct if the size of the source array is as long or longer than the destination array. But even slightly more complicated functions are harder to reason about correctly and are common sources of security vulnerabilities. Then say a future version of the Rust compiler is released with an optimization that targets this exact code pattern and renders the safe version just as fast as the unsafe version, which could very well happen in the next compiler release. Now, no matter which choice the library developer makes, there exists contexts in which that choice is not good. So, can library developers make bounds checking decisions that are correct for all possible contexts? They probably can't, but to answer this a bit more rigorously, we break this overarching question down into 3 more precise questions and evaluate them in a study. The first question asks, how prevalent is unchecked indexing in the Rust ecosystem? We first find that 10% of the 500 most downloaded Rust libraries use unchecked indexing, many of which are used in applications that prioritize safety. We also count the number of source-level unchecked indexing operations across a set of 27 popular, reasonably well-maintained, safety and performance-oriented Rust applications. 3 of these applications contain no unchecked indexing whatsoever. 8 contain unchecked indexing in the top-level application code, and 22 contain unchecked indexing in library dependencies. If one application depends on 100 libraries, and each library has about a 10% chance of containing unchecked indexing, then there is a greater than 99% chance that at least one dependency has unchecked indexing. This indicates that unchecked indexing is prevalent in the Rust ecosystem through application dependencies. The second question asks, within a specific context, is the use of unchecked indexing justified by performance? To answer this question, we perform the following experiment. Given an original unmodified library benchmark, shown in red, and a version of that benchmark where all unchecked indexing is converted to checked indexing, shown in blue, what is the performance difference between these 2 versions? The performance difference represents the overhead of bounce checks, so a larger performance difference is a better justification for eliding the bounce checks in that context. We performed this experiment for 7 libraries in the top 250 most downloaded Rust libraries, which amounts to running this experiment on 203 different benchmarks. We present our results as a histogram of the distribution of observed speedups. The majority of benchmarks are not significantly affected by the presence of bounce checks, which we can see by the clustering around the red speedup equals to 1 vertical line here. Almost 24% of benchmarks do improve when bounce checks are elided, meaning that these corresponding unchecked indexing operations can be justified in our context. Finally, almost 12% of benchmarks improve when benchmarks are added. This is very surprising, and while we have some theories for why this is the case, we are not yet sure why these are all faster. The bottom line is that while unchecked indexing can improve performance, most of the time it actually does not. The third question asks, is unchecked indexing justified by performance in all contexts? To address this, we perform a similar experiment as in before, but we benchmark a single sample application on 4 slightly different contexts, where each variation only changes one part of the context. The overhead of checked indexing in our baseline context on the far left is 7.7%. Using an older compiler version changes the overhead to 6.5%. Using a different architecture changes the overhead to 2.5%, and using a different workload changes it to 4.4%. This highlights that even relatively small changes in the context can make a huge difference. Note that all these values are relative performance differences, meaning that our sample application doesn't necessarily run faster on M1 architectures. Furthermore, since the safety or performance goals of applications are also a part of the context, different applications may have different acceptable overheads for bounce checking, even within the same software stack, so the decision to use bounce checks may be different. Ultimately, the decision to use unchecked indexing in one context cannot determine if it should be used in another. Since bounce checking decisions are context dependent, library developers can fundamentally never make bounce checking decisions that are correct for all possible contexts, yet they are put in a position where they have to anyway. Instead of making library developer bounce checking decisions correct, since they fundamentally never can be, what if we make those decisions on a per context basis? We present NADER, a new approach that enables application developers to control which indexing operations are bounce checked within their context, without changing the library developer workflow. At compile time, application developers specify a threshold value and a benchmark, and NADER automatically reintroduces as many bounce checks as possible subject to the threshold value. By specifying an infinite threshold, the safety-oriented application developer can use NADER to identify and convert all unchecked indexing operations into their checked counterparts. By specifying a threshold value of 0, the performance-oriented application developer can use NADER to leave out the bounce checks that significantly affect performance. and rerunning NADER in a new context enables applications to take advantage of opportunities available in those contexts. The basic workflow of NADER starts with an input benchmark and a threshold value encoding an application's safety performance goals. NADER then identifies all unchecked indexing calls and creates a new version of the application where all unchecked indexing is converted to checked indexing. NADER then compiles both application versions in the given context and measures the maximum overhead of checked indexing. If the threshold value is smaller than the maximum overhead, NADER resorts to several heuristics to reintroduce the maximum number of bounce checks subject to the threshold. Finally, it outputs a binary that is optimized for the application's safety performance goals. When the overhead of checked indexing is larger than the threshold, NADER finds a minimal set of unchecked indexing to leave in the application. This amounts to solving an optimization problem, but while an exhaustive solution would return the best order of bounce checks to reintroduce, getting it for a program with only 20 unchecked indexing operations would take almost 11 days to complete, so this is not feasible. Therefore, NADER instead primarily leverages a hotness-based heuristic, or the dynamic execution count of each instruction, to reintroduce a majority of bounce checks. It then switches to another heuristic called the unchecked slowdown to reintroduce the remaining bounce checks with the smallest overhead until the threshold is reached. We refer those interested in these details to section 4.4 of our paper. We go on to evaluate NADER on 10 popular Rust applications. For 2 of the applications, the original and fully converted binaries are identical, which is likely the result of the compiler eliding code that uses those added bounce checks. This means that adding bounce checks would not meaningfully improve application safety, so NADER returns them unchanged. For 6 applications, NADER finds that fully converted binaries do not perform significantly worse than the original binaries, so NADER returns them fully converted with a total of 712 reintroduced bounce checks. For the final 2 applications, NADER finds that fully converted binaries do add overhead, and we show that it finds minimal sets of unchecked indexing for various threshold values. For the cost application, NADER reintroduces 7 bounce checks without any additional overhead, 1 bounce check with an overhead of 3%, and the final bounce check with an overhead of 11%. For the Brotli decompressor application, NADER reintroduces 222 bounce checks with no additional overhead, 39 bounce checks with an overhead of 3%, and the final 2 bounce checks with an overhead of 7.7%. In summary, library developers are faced with the impossible task of making correct safety performance decisions for all possible contexts. We show that in the Rust ecosystem, library developers often sacrifice safety but rarely gain back performance in our given context. We develop a new approach called NADER that empowers application developers to step in according to context-specific needs. We show that our prototype implementation of NADER reintroduces hundreds of bounce checks with no additional overhead and enables better safety performance trade-offs in 2 applications. A few of NADER's limitations stem from the fact that it's a profile-based tool and is subject to the variability inherent in performance measurements. NADER also therefore requires that applications provide reliable end-to-end benchmarks. Applications whose performance is inherently variable are thus not good candidates. NADER also works on source code and so is not compatible with applications that are distributed as precompiled binaries. In many cases, we find that the bounce checks cost more than they should due to unnecessary compiler limitations. NADER currently works around these limitations by letting developers specify a tolerable overhead threshold, but in the future could be used for targeting expensive bounce checks and finding optimization opportunities through static analysis or other means. We could also extend our insights into an annotation for developers to hint to the compiler that some bounce checks may not be necessary and enable more targeted optimizations. Finally, NADER could also be used on other patterns of performance-motivated Rust code like SIMD instructions or inline assembly. Thank you very much.